Today we'll be preparing an ester, ethyl chloroacetate, and trying out an experimental way to make ester synthesis more efficient. To start, we're using the corresponding carboxylic acid that we required, chloroacetic acid, which as you can see is a crystalline solid. Be careful with this because it's quite toxic and a metabolic poison. Don't get it on your fingers. To esterified this we're going to use an excess of ethanol. Normally you'd use a very large excess, but we're going to try something different today and we're only using 150 ml, which is about a 3x molar excess. We'll add the ethanol to the chloroacetic acid and dissolve it. It takes a bit of stirring to get it all into solution, but it does eventually. We've set up the 500 ml flask. We put a stir bar in there because we originally thought we'd stir the mixture, but we don't actually need it. Some anti-bumping granules would be a good idea though. We've added the chloroacetic acid and ethanol to the flask. And now for our catalyst, we're going to use 3 ml of concentrated sulfuric acid. We added this to the flask, and then set up for reflux using a heating mantle. As the reaction occurs, water is produced, and together with the ethanol this distills off as an azeotropic mixture, condensing in our reflux condenser and then dripping back into the mixture. Our plan was to try to remove this water during the reflux process. This is calcium oxide. It reacts with water to form calcium hydroxide, which is also a solid. Both of these compounds are insoluble in ethanol. Let's see it react with a few drops of water. There's no obvious reaction, but the mixture heats up and you can see some steam being given off. We put an adapter between the flask and the condenser and placed a cut-down fluted filter paper into it like this. The idea is that the vapors can come around the sides of the paper, but the drops of condensing liquid will fall into the middle and filter through the paper. And we've placed some calcium oxide into the paper so that the ethanol will drip into this. It's important though that none of the calcium oxide makes its way into the flask. Calcium oxide is alkaline and will react with both the chloroacetic acid and the sulfuric acid catalyst. Okay, let's start heating and see what happens. Pretty quickly the mixture starts to boil. And we've got some reflux starting, which is dripping right into the filter as planned. But it's too much. The filter isn't capable of handling more than one drip about every 5 seconds. So we've got an overflow and some of the calcium oxide is coming with it into the flask. So we removed the middle adapter and just set up for normal reflux. After an hour we tried again using a different configuration of filter paper and with the calcium oxide packed down tightly. But this also overflowed after a while. So at this point we tried a different approach. So after another 30 minutes of normal refluxing, we set up for simple distillation. Only using calcium oxide in the receiving flask. We figured we'd collect the ethanol and water azeotrope and then try to dry it using the calcium oxide before returning to the boiling flask. With the azeotrope boiling off at around 80 degrees C, we've got the fairly quick distillation collecting, and the temperature of the receiving flask is getting quite warm due to the reaction of the water with the calcium oxide. After a while we poured out the mixture from the receiving flask and allowed it to settle. Then we replaced the calcium oxide in the receiving flask and continued the process. and once the mixture had settled we placed the alcohol back into the boiling flask. To be honest, this was all a bit of a pain in the ass because it meant constant disassembly and reassembly of the apparatus. And the product in this case is quite lacrimatory, which didn't help. After we continued this process for about 2 hours, we decided to switch back to simple distillation without the calcium oxide, and first distilled off excess ethanol from the reaction mixture. The ethanol was at distillation temperature gradually rose, and above 100 degrees C we changed flasks and collected another fraction. Then we collected a final fraction above 135 degrees C, with the vapor temperature rising to 144 degrees at its peak. The contents of the boiling flask began to char and turn black towards the end of the distillation. Once the speed of the distillation slowed down, we stopped heating. Here's our first fraction, which came off above 100 degrees. On adding water to this, we noticed that a bottom layer formed. It's a little difficult to see because the color is very close to the water. And on the right, here's our slightly off-colored fraction, which we collected over 135 degrees. Since the product appears to be insoluble and immiscible with water, we decided to combine the fractions in a separating funnel and wash with water. The organic layer turned slightly milky. We shook thoroughly, allowed the layers to separate, and then removed the bottom layer into a flask. Then we added some anhydrous magnesium sulfate to dry this. Here's our product: 55 grams of ethyl chloroacetate. We were interested to see how much we'd get, but despite our attempts at drying and recycling ethanol, this is only a 57% yield on starting chloroacetic acid. But this is not bad considering how much we messed around with the reaction. Be careful with the product. It's not as bad as bromoacetone or bromopropiothenone, but it's lacrimatory and worse than benzyl chloride in that respect. There may be a way to use calcium oxide to make esterification more efficient, but it's going to require some more specialized equipment, and also having the oxide in solid granule form so it doesn't wash over. We'll let you know if we get anywhere improving this.